In this video, I want to talk a little bit more about covalent bonds. And remember that covalent bonds are bonds in which the bonding electrons are shared between the two atoms. So the bonding electrons are shared between the atoms in the bond. However, they do not have to be shared equally. So one of those two atoms can actually have a greater share of the electron density. When that happens, we have what are called polar covalent bonds. So two types of covalent bonds, nonpolar, and in nonpolar covalent bonds, our electrons are going to be equally shared, and then polar covalent. So nonpolar, the bonding electrons are equally shared. Between the two atoms. In the bond. So an example, if I was to draw a bond between two hydrogen atoms, I'm going to have hydrogen and then another hydrogen. And I'm going to use dots to represent those two electrons. We're going to talk more about this later on in this chapter, but right now we're just going to use those two dots to represent electrons. And a single bond actually is two electrons, so two dots. And if we were to measure the distance between the nucleus of one of those hydrogen atoms and those electrons, and the nucleus of the other hydrogen atom and those electrons, it's going to be equal distant. So those two electrons are found, kind of halfway between the two atoms. They're going to be shared equally. So that bond would be considered nonpolar covalent. A polar covalent bond and these are under covalent bonds. I didn't write covalent bond here, but they are under this category. If you want it there. So a polar covalent bond, our bonding electrons are not shared equally. They're still shared, right? It's not ionic, it's still covalent, so we're still sharing them. It's just that one of the two atoms has the greater share of that electron density. So the bonding electrons are not equally shared. Again, still shared, right? It hasn't become ionic, but they're just not equally shared. Right? One of those two atoms gets the greater share of that electron density. And an example, if I wanted to show the bond between hydrogen and fluorine, those electrons are actually found closer to fluorine's nucleus than they are to hydrogen. They're still shared, right? They're still found between both of them. Sometimes they'll show, I'm not a big fan of the circle thing, but sometimes they'll show circles around them, right? We can show how those electrons are being shared, right? They belong to both hydrogen and fluorine. Here they belong to both hydrogen. And in this example, they're in the middle, right? They're equally shared. And in this example, fluorine has the greater share. Again, be really careful. Hydrogen still has a share, right? It's not ionic, but fluorine has the greater share. Sometimes, like tug of war will be used as the analogy. So if the two hydrogens were playing tug of war for those electrons, the little piece of tape on the rope, right, is found right between the two. Like nobody's winning. They're equally strong, so they're pulling on them with the same amount of force. So those electrons, right, the little piece of tape on the rope is found there. If hydrogen and fluorine were playing tug of war for those electrons, fluorine is actually stronger in this case, and that piece of tape on the rope is closer to fluorine. Now, hydrogen's still holding on to that rope, right? It's not ionic. And then if I had a bond between, let's say, sodium and hydrogen, that would be an ionic bond. In this case, hydrogen's the stronger one, and hydrogen just pulled those electrons right away from sodium, right? And has won the tug of war. So kind of a stalemate, right? fluorine's winning but has not won. And then if it's ionic, right, one of the atoms has actually taken those electrons. It's won the tug of war. So are my electrons equally shared, unequally shared, or just not shared anymore, right? This would be ionic, no longer shared. Right, electrons not shared, right? One of them has taken them. So what determines, right, what atom gets the greater share, what determines whether or not they're equally shared? It's going to be based on electronegativity. And electronegativity is capitalized, or sorry, is abbreviated a capital EN. Sorry about that. And electronegativity is defined as the affinity that an atom in a bond has for the bonding electrons. So be really careful not to get electronegativity messed up, right, with the electron affinity energy from our last chapter, right? Electron affinity energy is the amount of energy that's released when an atom gains electrons. It's just an atom gaining electrons. Here, I actually have a bond. Electronegativity only applies if we're talking about bonds. So the electronegativity that an atom in a covalent bond has for those bonding electrons. So how, the more electronegative it is, the more it's pulling on them. Affinity just means like it wants it. So the more electronegative it is, the more it wants those electrons. So if I go up and look at this example again, fluorine is going to be my more electronegative atom. It's pulling on those electrons more. It wants those electrons more. If I looked at this one, hydrogen is actually my more electronegative atom because it's taken those electrons. So the real reason, so anytime you see this delta in front of something like this, it's going to mean a difference. So this is my electronegativity difference. The real way to tell if a bond is going to be covalent or ionic is based on the electronegativity difference. Remember I said for us, a metal and a non-metal, unless we have polyatomic ions, will be ionic bonds, and then non-metal atoms will be covalent bonds. The real reason is an electronegativity difference. It just happens that the electronegativity difference between metals and non-metals is so great that it's ionic. And the electronegativity difference between a non-metal and another non-metal is smaller, so it happens to be covalent. You could have, a covalent bond between a metal and a non-metal if the electronegativity difference is small. So the difference in electronegativity between the two atoms is really what determines whether a bond is covalent or ionic. And then if it's covalent, it's what's determining whether it's polar covalent or non-polar covalent. So electronegativity difference between the two atoms in a bond determines if the bond is nonpolar covalent, polar covalent, or ionic, right? If that electronegativity difference is great enough, then one of those atoms has just taken the electrons from the other, and it is an ionic bond. I'm not worried, there are numbers, if the difference is, greater than 2 or between 0.4 and whatever. I'm not so worried that you know those numbers. I just want you to know that that is the difference between what type of bond we have. And then I do want us to be able to determine if a bond is going to be non-polar covalent or polar covalent. That we do need. So a rough sketch of the periodic table here, incredibly rough. These are my noble gases, so group 18 or 8A. I'm going to ignore those. And then fluorine is right here. Fluorine is the most electronegative atom we have, And with a couple exceptions, as we go closer to fluorine, it's going to become more electronegative. So if I was to compare carbon to fluorine, fluorine is more electronegative. It's going to have the greater share of those bonding electrons. If I was to compare carbon to nitrogen, nitrogen is closer to fluorine. And again, we're just using the trend here. We're not going to explain this trend. So you can just really look at its position in the periodic table. Nitrogen's closer to fluorine. It's going to be my more electronegative atom. That's not why it's more electronegative, but that's how we're going to remember it. Hydrogen is often an exception. So hydrogen's over here. I'm just going to cross them off. Hydrogen has the same electronegativity, and we do need to know this, as phosphorus. So when I'm looking at the trend on the periodic table, I'm going to imagine hydrogen right over phosphorus. So if I was comparing nitrogen to hydrogen, nitrogen is closer to fluorine than phosphorus is. Phosphorus is where hydrogen is in that trend. So just imagine hydrogen right over phosphorus. And then because I said you didn't need to know the actual numbers for the cutoffs, whether it's nonpolar, polar, covalent, or ionic, I'm just going to tell us a couple nonpolar ones, and you'll just memorize this incredibly short list. And then if it's a covalent bond that's not on this list, it's going to be polar covalent. There are others that are not on this list, but I will stick to this one. It's pretty short. So nonpolar covalent bonds. And again, there are others, but these are the ones I want us to remember. So something in itself, I'm just going to use Z as a generic atom. It doesn't matter what it is. But if you bond an atom to the same atom, those two atoms have the same electronegativity, right? Hydrogen has the same electronegativity as hydrogen, so they're going to pull on them with equal strength. Carbon has the same electronegativity as carbon, so they're going to pull on them with equal strength, right? Sulfur bonded to sulfur, they have the same electronegativity, they're going to pull on them with equal strength. So anything bonded to itself is what that's representing. And then carbon and hydrogen, there is an electronegativity difference, but it's so small that it's under the cutoff. So it's not completely like equal, but it's equal enough that it's considered nonpolar. So carbon-hydrogen bonds are going to be considered nonpolar. And then remember, hydrogen has the same electronegativity as phosphorus. So that's going to be nonpolar because they're pulling on them with equal strength. And then one more by association. If carbon-hydrogen bonds are nonpolar and hydrogen has the same electronegativity as phosphorus, carbon and phosphorus bonds are also going to be considered nonpolar covalent. Other covalent bonds that I give you, we're going to assume they're polar unless I tell you otherwise. So delta notation, this is what we're going to use to indicate polar covalent bonds. So this is the notation used to indicate polar covalent bonds. And there's three parts to the notation. Our first part is we're going to have a partial negative symbol. So this is a lowercase delta. So a lowercase delta with a negative sign, and the way that we read this is we would call it partial negative. So we're going to identify the partial negative atom. You can't just put a negative on it, because if you did, that means it would be ionic, right? It took those electrons, and it hasn't. My partial negative atom is going to be my more electronegative atom. So it's not negative, it's just kind of negative because those bonding electrons are closer to it. Right? If I went back up and look at that HF example, get rid of some of this stuff, right? Those bonding electrons are closer to fluorine. Fluorine is my most electronegative atom, so it's going to get my delta negative, right? My partial negative charge. So partial negative, this is going to be my more electronegative atom. So in the bond, which of the two atoms is more electronegative? That's going to be my partial negative one, right? The bonding electrons are closer to it, so it's kind of negative. And then our second part is we're going to have our partial positive. That's going to be the other atom in the bond. So delta symbol again with a positive charge. This is going to be the less electronegative atom. Right? The bonding electrons are further from it. It still has a share, so it's not positive, right? It hasn't lost them. It's just kind of positive because the electrons aren't as close to it as it is to the partial negative atom. And then the last piece of notation, and you do need all three pieces when you're doing this, is an arrow. And then it has like a little cross at the end. So an arrow with this little like cross. So don't forget that part, that is important. Otherwise, it's not the correct notation. And this arrow is going to go from the partial positive to the partial negative. It's showing the direction that the electrons are being pulled. So goes from the partial positive to the partial negative. It's going to show the direction that the electrons are being pulled. Right? If you want to go back to that tug of war analogy, that's the direction the rope is going, right? It's being pulled towards the stronger one, which is my more electronegative atom. So I'm just going to rewrite that hydrogen and fluorine example. I'm just using a line now instead of two dots. One line is a single bond is two electrons. And we'll talk again in more detail later on in this chapter about that. But I'm going to assign polar covalent bonds to this using delta notation. So I know fluorine is my more electronegative atom, and I know that because I'm just looking at the periodic table and I'm looking at the trend. Fluorine is my most electronegative. Hydrogen then, of those two, is less electronegative, so it's partial positive. And then I have to add my arrow. It's always going from the positive to the negative. And it doesn't matter where you write them. Like I did the partial positive and partial negative on top and then the arrow on the bottom. If you want to like do them both on the bottom, that's fine. If I wanted to do this part on the bottom, I did that backwards, that part on the bottom and this part on the top, it doesn't matter as long as it's really obvious when I grade it that there's a partial negative on fluorine, a partial positive on hydrogen, and the arrow is going from hydrogen to fluorine. Let's do just a couple more examples. So if I have a bond between carbon and chlorine. So I want you guys to label this using delta notation. So just hit pause, put your partial positive, partial negative, and your arrow on it. And then when you're ready to check, hit play again. Okay. So to determine which is more electronegative, I'm really just looking at the periodic table. Chlorine is closer to fluorine than carbon is. So chlorine is my partial negative, carbon is my partial positive, and those electrons are being pulled towards chlorine. Let's do another one. How about phosphorus and carbon? I'm going to give you a couple here. Let's do oxygen and hydrogen. Okay, so again, if they're polar covalent, we want to assign partial charges, right, using delta notation and our arrow. And then when you're ready to check, just hit play. Okay, so this one, carbon and phosphorus, are actually on my list of things that are non-polar covalent bonds. So I'm actually not going to assign delta notation to this, right? They have very similar electronegativities. They're so close that the bond is considered non-polar. So no notation on this one. If it's non-polar, we're not going to include it because delta notation is our notation used to indicate polar covalent bonds. So that one, if you were confused as to what to do, that's why. You don't do anything with it. And then oxygen and hydrogen, Remember, hydrogen is where phosphorus is in the periodic table. So oxygen is closer to fluorine. It's my more electronegative atom. Hydrogen then gets my partial positive, and then the arrow goes from hydrogen to oxygen.